Welcome to the latest episode of the MFG Radio Network's Manufacturing Matters, where industry experts take deep dives into the latest technologies you need to consider to keep manufacturing moving.
Hello, and welcome to Generation of Titanium Material Allowable Data for Laser Powder Bed Fusion, brought to you by Aerospace Manufacturing and Design Magazine and 3D Systems. I'm Eric Brothers, editor for the magazine. 3D Systems has generated a high-fidelity data set, including a wide range of mechanical and material properties for aerospace titanium alloys printed on the DMP Flex 350 laser powder bed fusion printer. The full data set includes raw data for tensile, fatigue, pin bearing, shear, compression, chemistry, microstructure, and more. This data may be useful to accelerate machine, material, and part qualification for critical applications, perform a delta qualification for new machines to demonstrate equivalence to the dataset, or add to internal datasets for laser powder bed fusion of metals process qualification. We'd like to thank this webinar sponsor. 3D Systems offers a broad portfolio of additive manufacturing hardware, software, materials, and service solutions from plastics to metals. Their global application innovation group reduces risk and creates a faster return on investment for customers by developing qualified, transferable, and scalable production processes. A few words about our presenters. Dr. Mike Shepard, VP Aerospace and Defense for 3D Systems, is an aerospace metallurgist specializing in fatigue and fracture. Mike spent 16 years at the Air Force Research Laboratory in Dayton, Ohio, where he led the behavior and life prediction section and ultimately the aircraft structures technology branch. During his time in these organizations, he led efforts to develop new technologies and solve field issues for turbine engines and airframe structures. He now leads 3D Systems Aerospace and Defense segment, helping customers rapidly design and produce additively manufactured components for aerospace and defense applications, accelerate the certification process, and optimize their entire supply chain. Ryan Fischel, a process and validation engineer with 3D Systems Application Innovation Group, concentrates on machine qualification and print process development for laser powder bed fusion. With a background in several modes of additive manufacturing, or AM, in plastics and metals for the aerospace and medical industries, Ryan is focused on advancing the state of the industry to increase AM usage in many types of critical applications. You may ask questions by typing them into the question box on the bottom of your Zoom screen. Welcome, Mike and Ryan.
All right. Thanks for that kind introduction, Eric. I appreciate it. We thought we'd start today's discussion with a little bit of philosophical underpinning, right? So I think that as a community, we recognize that additive manufacturing has really matured nicely and is finding productive use in some pretty serious applications, right? So say healthcare, right? Where you're talking about the potential for a medical device to be implanted permanently in a patient. Perhaps aerospace, right? So you have a situation where you may have a safety critical application, or perhaps an application where function is very critical to mission success. So integrating new manufacturing processes into these types of applications, it's not our first rodeo as a technical community, but typically this work involves very significant complexity, right? So with any new manufacturing process, like additive, one of the first things that you're going to need to do is you're going to need to establish the overall process capability for the underlying process. So for our purposes today, we need to decide if we're creating good metal, right? And is the process robust and consistent? Once a process is stable, so you've decided where you're going to set all the knobs on the manufacturing process, the first step you normally go to after that is you begin to develop very large data sets. So these are carefully thought out, well pedigreed data sets. Often these are termed allowables. So as in mechanical design, the allowable stresses, the allowable strains, that type of thing, right? And then you're going to be using those to determine your mechanical design limitations, right? So what are some of the requirements for these data sets? So first of all, the data sets, they need to support all of the ancillary and adjacent functions in an organization. So that could be things like not just the engineering process, but also important quality control functions. And there may be regulatory requirements, say with the FAA or EASA or the FDA, right? Secondly, you need statistically significant data sets. So you have to have enough data so that you understand not just the typical performance of the process, but you also need to understand lower bound or worst case behaviors. That's all very important. And then the experiments need to be set up so that you're capturing all of the expected process variation that you would see in normal production, right? So for laser powder bed fusion, that would be things like the powder lot, the use of a different machine, perhaps a different facility, or where the part or specimens are located in X, Y, and Z space inside the build volume. We have also found that it's extremely useful and in fact, sometimes required to really be utilizing published standards. This really ensures that you have maximum transparency inside the data set, and that allows for comparisons with external work that may be going on. So in terms of the process variables and things like that, you would be looking at requirements that might come from SAE or ISO or ASTM. And then for the testing that you might do, mechanical testing and otherwise, you'd be looking at things like ISO and ASTM testing standards. At 3D Systems, we've also found that it's extremely useful and perhaps a best practice to use certified test providers, right? Especially those who are going to be qualifying their uncertainty. And that's really useful because they're going to have certifications like ISO 17025 or NADCAP. It's going to make sure that they're really well qualified to carry out the tests in question. And as a third party, they're not going to necessarily have a vested interest in the particular test results, right? So they don't have any conflict of interest. Next slide, please. All right. So let's talk a little bit about the test setup. Next slide. For the purposes of today's discussion, I'm going to presume that most of the folks online here understand laser powder bed fusion. If that's not the case, feel free to Google it right on the side. You're going to get lots of good information. But for this exercise, we're using the 3D Systems incarnation of laser powder bed fusion, which we call direct metal printing. So the key difference with direct metal printing is that we use a very low oxygen build environment inside our machine architecture. And it's typically less than 5 parts per million oxygen. So that's very, very low for laser powder bed fusion. I think we mostly recognize that laser powder bed fusion is a welding operation, albeit a very fancy welding operation, but welding nonetheless. And most of us are probably also going to recognize that if you can choose to weld in a lower oxygen environment versus a higher oxygen and interstitial environment, it's better to have less oxygen. So the machine we've used is our DMP Flex 350. That's our standard single laser mid-frame system. I'd say it's larger than average in terms of a mid-frame system. The build volume is 275 millimeters by 275 millimeters by 420 millimeters in Z. Of course, there has to be a build plate in there as well. And it can easily process a wide variety of metals, many of which are indicated here on the PowerPoint chart. So for this work, we've focused on Ti grade 23, which many of you will know as Ti 6 aluminum 4 vanadium extra low interstitial, or sometimes called rotor grade Ti 6-4. So this material it's got really excellent ductility, it's got great toughness, and it's often chosen for healthcare and aerospace applications because of that high level of damage tolerance. So with that, I will turn the floor over to my colleague, Ryan, and he is going to walk you through a little bit more information from the data set.
Yeah, thanks, Mike. So I wanted to walk you through some details of the test matrix, and we'll go in through quite a few details of them. So as part of this allowables material data set generation, we need to generate a large variety of mechanical data. So I've got some of that shown in the table here to the right. Today, for the sake of time, we're going to focus on tensile and high cycle fatigue. And in addition to determining what sort of data are we going to generate, we need to generate, well, how much of it and what sort of test groups are we going to have. So in order to determine how much data we were trying to generate, we followed an existing framework. Many of you are probably familiar with MMPDS. Mike is actually on the Industrial Steering Committee for MMPDS Volume 2. So this is the new currently draft volume that includes additive manufacturing. And what we decided on is kind of a modified version of what MMPDS recommends, which is a modified S basis in terms of the number of powder lots, the number of machines and build cycles, et cetera, but increasing the statistical sample size. So we want to have a very good statistical basis for making the judgments that we have. So we actually went well above and beyond what is required for what is now called C and D basis. Those are familiar. That used to be called A and B basis. And some of the key things that are trying to be captured by these numbers of heats and lots, machines, build cycles is the in-process variability. And you can maybe see that we're also capturing things like different orientations, different temperatures. We're really trying to see what is going on with the additive manufacturing process. Can we quantify all of these effects? So kind of leading into that is what are some of the sources of process variability? Mike had a great introduction with some of that. Things like your raw material, things can potentially vary between lot to lot or supplier to supplier even. Your machine, sometimes you have some differences in your machines. Anyone who's worked with industrial equipment knows that they can sometimes have some personalities. Your geometry and orientation, is it oriented horizontally, vertically towards the build plate? Is it some sort of organic shape? What about your build plate location? Is it the front, back, left, right? Is it tall? Is it short? These are all going to affect your part. What about your post-processing? Are you doing any sort of heat treatment after your part? So here we're talking about a HIP. This is only going to be HIPed data from a single supplier, although we do have multiple runs from that single supplier. And then your powder reuse, especially with reactive alloys like titanium, they tend to pick up oxygen quite readily. And so those who are familiar with laser powder bed fusion know that powder reuse for titanium is especially big topic. So we really, I think the key point in this big blue box is to capture your expected process variability. How is it affecting the material properties throughout this test campaign? A little bit more on powder since we've talked about it. Everything that is done for this study is what we're calling our laser form powder. Laser form just means that we've qualified the powder. So this is powder specification that has been used for many years at 3D Systems to generate medical devices, aerospace components, industrial, a whole variety of components that we've seen excellent results from. As Mike mentioned, this is the extra low interstitial variant of Ti64, otherwise known as grade 23. It's plasma atomized and it meets the requirements of ASTM F3001, as well as our own internal specifications. But before we go into entire data set generation, we need to confirm that the powder is actually behaving and performing as we expect. So we do things like check the flowability of the powder, check the spreadability of the powder, make sure that we can deposit a good layer of powder, and then actually print with it. So we do a build and make sure that that powder is performing as expected based on our years and years of experience with working with it. As far as powder handling, after each subsequent build, this is part of our standard practice, is we did open air sieving and we topped off with virgin powder. So in the additive manufacturing process, of course, you're using some powder, you're losing some powder during your sieving. And so we added in virgin powder to maintain our level of powder in the machine. And then finally, on the powder side, one of the key things, as I mentioned, is that oxygen pickup over time. And so in order to quantify this, 3D Systems had done a study on oxygen pickup over time. So every single build, powder oxygen is measured. This is part of our standard practice. And we found there is a slight upward trend, as you can see, over the course of a year. So this is about 70 builds that we measure the powder oxygen of with a slight upward trend, but what we found is that after a year, we actually exhausted the entire powder lot. So this is usually around 1,200 kilos of powder. And so that low oxygen printing environment is really the key there. That's where you have the highest risk for oxygen intrusion into your powder. And even after a year and many dozens of sitting operations and builds, we were still under that grade 23 threshold.
So I'll just foot stomp Ryan's point here. Reuse of powder is really an important topic. It's well supported by that low oxygen architecture we're going to be talking more about as we move forward. A kilogram of powder is $200 or something like that per kilogram, right? So you don't want to leave any powder on the table, and the low oxygen architecture helps make sure that we can use every gram of powder.
Yeah, absolutely. So let's get into a little bit about the build. So we saw a picture of the real life build on the opening slide. Here we've color coordinated it just for some ease of visualization. This is the main build file that we use to generate all this data. So a few things to point out. We'll just focus on the tensile bars in blue just for a second, is we have some horizontally oriented bars. So in other words, this gauge section or this test kind of central axis is parallel to the build plate. And we've built these in stacks as blanks. So these are essentially hexagonal prisms that are later machined per AS10E8. We've got some vertical bars here, and then in the back, a little bit tough to see, admittedly, some 45-degree bars oriented relative to the build plate. A lot of fatigue coupons here as well. You'll notice that everything here is across all different parts of the build plates, the corners, the center, the sides, and that's just part of capturing some of that in-process variation. We have magenta coupons. These are some witness kind of material characterization. Some of these are solid supported to the plate, so they're kept on during the HIP process, and then some were removable support, so we could have the pre-HIP and post-HIP data for things like potentially chemistry or microstructure or whatever else we were trying to look for. Another is this lattice coupon. This is a process monitoring coupon that we have across all areas of the build plate at the bottom and the top. We found that this is an extremely sensitive coupon for process monitoring that we're able to kind of use as a canary in the coal mine to see if there's anything going wrong with the process before we go through an entire test campaign. And then finally, we have some powder traps and of course supports in between the parts that are removed. And all of these parts have a unique label on them. It's a little blurry in this picture, but there's full traceability of all of these parts back to the machine, the build, the orientation, location, etc. So going into a little bit about our production overview, we, as I mentioned, use 3 machines across 2 different sites. So 2 of the machines are in Littleton, Colorado. This is where I sit. This is our kind of additive manufacturing metals center of excellence in the United States. And then one of them was in Leuven, Belgium. That's our center of excellence for Europe. And both of these are AS9100 certified facilities. We do tons of production at both of these facilities, as well as some process development. And all of these machines are pre-qualified going into this test campaign with our standard IQ, OQ, PQ process. Some of you might recognize that, but if you don't, IQ is the machine plugged in? Is it working with facilities and things like that? Your OQ, is it working at the edges of the process window, kind of a worst case, if you will? And then PQ, or performance qualification, is the machine producing at nominal conditions. Each one of these machines did have just one powder lot, so there was no mixing of powder lots amongst machines. And then in order to capture the variability in the X and Y location, we rotated the build by 90 degrees every single replicate. So there are 4 different builds, all with the same coupons, just rotated 90 degrees counterclockwise. So a sample that maybe was in the back to start ends up on the left, and then the front, and then the right, to capture things like maybe gas flow or laser focus or any other sort of deposition variation that we might see. And finally, before we get to the results, I'm sure everyone's dying for them. Just to get into a little bit of the post-processing workflow, after a build was taken out, it's depowdered, remove any excess powder, and then we remove those as-built witness coupons. So those are your powder traps, your lattice coupons, and then about half of those magenta witness coupons. We then brought it out to an external partner where everything was hipped at 900 degrees Celsius on the build plate. And so this is done in order to relieve all the stresses while the parts are still directly welded to the build plate, as well as all the benefits of the hot isostatic press process. Afterwards, all parts are removed via wire EDM, and then those stacks are separated via bandsaw. Those parts are then sent out to our externally accredited test partners. Mike mentioned earlier, those NADCAP and ISO accredited test partners. And since these are all printed as blanks, all of those testing partners did perform CNC machining for those sample preps. So for tensile, it's just machining. And then for our fatigue, it also includes a low stress grind operation.
So just could you
All right.
just jump back, Ryan? Yeah, there you go. All right.
Absolutely.
So kind of rolled into the discussion here. As we've gone through this exercise, there's just some important decisions you need to make about what your choices are going to be for the experiment and for the metals you selected. So the 900C hip that we selected there, right? You might see Ti-64 used in other incarnations, right, with a slightly different hot isostatic press treatment, or perhaps no hip at all whatsoever if you were going for a very, very high strength condition. These choices are just necessarily rolled into the test matrix, but we're reporting some of the choices that we made. And in many cases, you're going to find that these correlate with practices that are very, very common in either aerospace and or healthcare applications. Thanks, Ryan.
Yeah, absolutely. I think it's a great point. All right, getting into some results. I'm sure everyone's been waiting for this. So just to tantalize you a little bit more, we had all of these bars were machined to ASTM E8 size 3, and of course tested per ASTM E8 by those externally accredited partners. And the bulk of the data here that I'll show you is focused on room temperature, but we also did go across multiple different temperatures from cryogenic all the way up to 500 degrees Celsius, and broke up our test groups by orientation. The reason for that is just the nature of the layer by layer growth of additive manufacturing laser powder bed fusion is those grains are going to grow differently in a horizontally oriented bar versus a vertically oriented bar. So this was how we decided to group our test groups and see what the effect on that was. And of course, everything is tested across these multiple machines, multiple locations, once again, trying to capture that inherent variation, have good confidence in our process. So getting into our plots here, this is the pooled tensile results. So this is all 394 data points that we have to offer as far as tensile at room temperature. So this is combining all of those different variables that we've brought up a few times now. And I think some of the key things to look at is just how small these box plots are. This was actually something that was quite refreshing as we reviewed the data, is looking at a really small standard deviation and coefficient of variation on this data set. So even with all of this brought in variation, the data set variation is quite small. The second thing to point out is that this data is in line with our published data. If you were to look up 3D Systems Titanium, you can find all of these values of our reference lines, and everything is right in line with what we expect plus or minus our standard deviations. The third is what I'm listing here as an AMS 4911 reference. So this is data taken from the Mill Handbook 5, which later became MMPDS. So this is the T99 or the A basis value for some AMS 4911 titanium. So this is a wrought plate of annealed titanium. So the better comparison, this is not necessarily an average, this is the T99 value, or essentially the lower bound of that value. So if you take a look at the lower bounds of our box plots, that is kind of your best reference for an apples to apples comparison with that AMS 4911 data. And then finally is the ASTM F3001. So this is the minimum specification for additively manufactured Ti-64. So we need to take a look. Hey, are there actually consistent tensile properties across our main process variables? Looking at printer orientation, plate location, Z height, powder reuse as some of the main ones. And some of these major variables. So ultimate tensile strength and yield strength, kind of looking at those units measured in megapascals, and then elongation to have a measure of ductility. So I'll show you one of them here, looking at the room temperature data versus printer. So our 3 different printers, once again, these are across 2 different sites and 3 powder lots. And when looking at this data, there's actually no practical difference between any of the printers. And by practical difference, what I mean is, even though you see some slight variation in the heights of these box plots, the means differed by no more than 20 megapascals. So this is within kind of your typical like measurement error or a kind of gauge R&R of tensile testing. And anything that's less than that is not really something that's practically significant as far as an engineering judgment is concerned. And this the same trend of being well above that MMPDS and reference, as well as the ASTM F3001 reference, still applies here. So we're really happy to see that there's very little difference across our data. Everything is still in line with what we expect and have seen. So we did do a evaluation of all of these mechanical properties across the main process variables and found that for all of these main process variables, we saw no practical difference observed. Once again, those fairly small differences gives us quite a bit of confidence that printing of Ti-64 on the DMP Flex 350 is extremely stable and consistent across many of these variables, many of which that can be altered by the user. So this was something that was quite encouraging for this data set.
And so by no practical differences, right, on the occasions when there are statistically significant differences between means of these various populations, the difference in those means was just as Ryan has referenced, very, very small, right? So not too many megapascals, 20 megapascals, and a very few KSI, for example, 2 or 3 KSI. So not numbers that are going to make any particular difference in an engineering design, and generally inside the uncertainty that you see in the mechanical property testing.
So I brought up earlier that we have some tensile data across various temperatures, and key that I want to focus on here is the shape of these 2 graphs. So the left graph is the absolute numbers of UTS across temperatures, once again, cryogenic through 500 Celsius. And then the right graph is each of their own data sets normalized to their specific room temperature, ultimate tensile strength. And so the key here is that the shape of these graphs is the same. There's no new physics going on. As you go up in temperature, you get the same temperature knocked down for both wrought material and laser powder bed fusion material. So once again, there's some consistency with that trend. We are confident that we're producing metal that is, going to behave similarly to your wrought titanium that's been used for many decades now. All right, let's get into a little bit of the fatigue results. As a quick review of our test matrix and fatigue, this is all axial, high cycle fatigue, load controlled using a servo hydraulic frame. I've got a picture of our test setup here. And all these blanks from our additive manufacturing process were machined in the low stress ground by our test partners. All of our testing was done at room temperature. And as far as test parameters, once again, high cycle fatigue done at 20 Hertz with a 10 million cycle run out value, fully reversed load, so full tension to full compression, and then 5 loads with 5 samples each per orientation. So once again, using those orientation groups as a test group. looking into some results. So for 74 total samples, here we got a nice looking SN curve, something that is really quite consistent with what you'll see with a lot of other SN curves for both additive and wrought titanium. And looking at runouts, we're seeing runouts in the neighborhood of 500, 525, gives us about 100% runouts. We even saw 1 or 2 runouts at the 550 megapascal level for this fully reversed high cycle fatigue. But when looking at our 3 different orientation groups, for statistical or practical differences between them, we actually found no statistically significant difference between any of our orientations. Certainly wouldn't be complete without comparing it to some historical data though. So on the left, you've got the graph that I just showed you, and then on the right, this is taken from the Mill Handbook 5 Rev J. So this is some historical publicly generated data that's been used for many, many decades now. This is of fully reversed high cycle fatigue using wrought annealed titanium. I think the few things that I just want to point out are 2 green circle or ovals that I have on here. The one on the left shows the stress levels that 3D Systems tested, and we don't have a full comparison one-to-one on there, but I'll tell you that at those stress levels, the additively manufactured cycles to failure given the same stress showed an increase in the life, the fatigue life of those specimens. And then looking at the runouts, you can see the Mill Handbook 5 data, we're seeing runouts in the neighborhood of maybe 45 to 60 KSI here for that kind of 10 million cycle runout regime. Whereas the additively manufactured data was seeing runouts in the kind of 70 to 80 KSI range. So we're showing longer lives at similar stresses and runouts at higher stresses. And I think what that kind of shows is that well-executed laser powder bed fusion compares favorably to historical wrought Ti-64, and it's showing kind of similar, comparable shapes to these graphs. And look, the data in Mill Handbook 5 has been used to design defense projects for many decades now. It's data that's well trusted by many in the public, and showing that laser powder bed fusion can both be comparable and perhaps even exceed that data is quite encouraging for the laser powder bed fusion process. And now I will hand it back to Mike to close it out.
All right, Ryan. Thanks for that. I appreciate it. So some exciting results there with the DMP process. So we've shared a bit of the data now, right, from the new allowables data set. I think that, we focused on the monotonic properties, the tensile properties today, the high cycle fatigue. There's a wide range of other data that's available from the data set. And the data it's now available for licensed use. So if you're interested in that, certainly you can reach out and we can discuss that. So how might we use the data? Well, perhaps you're looking to introduce laser powder bed fusion, the direct metal printing process in a new design. You're looking to start from scratch, right? So totally new application, right? Or perhaps you have a design and you have significant internal or external regulatory questions, and you're trying to grind through that, and you need more data, right, to support those adjudications. A third type of scenario, looking at a delta qualification type scenario. This is when you're looking to introduce perhaps a new manufacturing process like DMP, laser powder bed fusion, or you are looking to qualify a new machine to do laser powder bed fusion. In that type of delta qual situation, right, you're going to need a large data set that allows you to make comparisons between the legacy process and the new process to make direct comparisons about the machines and the process comparability, right? And then if you're going to do that, of course, starting with an existing data set that's highly pedigreed and has all of the raw data available associated with it, that's going to save you significant time and money versus doing that yourself. And then perhaps the fourth case that we have there on the slide, a little bit more esoteric. Maybe you're trying to understand the laser powder bed fusion process and whether or not it's applicable to your design scenarios, to your products, to your applications. The data that's in this data set is really going to be very helpful for that tire kicking kind of exercise where you're trying to understand the process capabilities of laser powder bed fusion and whether it's a robust, reliable process that you can use inside your applications. Next slide, please. So before we wrap things up, before we start with the question and answer period, we've shown you our approach at 3D Systems with respect to generating a large tailored data set that's useful for allowables generation activities. We showed that to you in our direct metal printing process. And we were showing the work with Ti-6 aluminum for vanadium. So I think it's clear that we've delivered from some excellent metal per the results that Ryan shared with you, and also that the process is robust and reliable and very insensitive to the known processing variables inside the laser powder bed fusion process. So we're very excited about the quality that we were able to achieve with the DMP process, and we're pretty excited that the mechanical properties are also comparing very favorably with respect to the additive manufacturing standards that are from most of you are familiar with, and they also compare very favorably with some of the historical data that we presented from the Mill Handbook 5 reference. And then in the last slide, we covered a couple of use cases that might make this data set useful. So with that, next slide, please. If you are interested in discussing this more, certainly there is a web link that you can use to get more information. There's also a QR code there. I tested it myself. It'll get you to the right place on the internet. So feel free to tie into those locations there and reach out, and perhaps we can have an additional discussion about the data set or how you might be looking to use that. With that, I'll turn it over to you, Eric, and I think Ryan and I will be glad to field any questions.
Well, thank you, Mike. Thank you, Mike and Ryan, for providing us with that detailed look at the laser powder bed fusion with titanium and what it takes to qualify it. I do have a couple of questions. Some of them are kind of basic procedural type things, such as how many coupons were built and tested to create the database?
Yeah, in total, we have over 500 data points. So that's spread across the bulk of which is in tensile, but certainly across the multiple fatigues and bearing, shear, compression, etc.
Okay. Another question was, what's a powder trap and how does it contribute to the mechanical property database?
Yeah, so a powder trap is just meant to capture the powder, and I can show you, but essentially, as you go through the process, you build like a cage around the powder. And so as when you're done with the process, if you want to say, hey, look, did anything change within the powder during the process or across multiple builds, we can open up those powder traps, pour out the powder, and do whatever testing it is you're looking to do, whether it's chemistry or flowability, particle size distribution, whatever it is.
Right.
So no impact on the mechanical properties, I should have said.
There is one. One of the things about the PSD is sometimes so there's going to be a sieving operation before the powder is used again, right, to get out undesirable powder where the morphology has changed or where it's now too fine or too coarse. So it's good to understand that morphology change. Our process is pretty dialed in at this point, but processes that are not fully optimized, sometimes you can create very large powder particles and you can create excessive fines. And so those, you'll lose those during sieving, but they can be quite a costly loss, in powder. So sometimes you're going to want to use those powder traps to really reflect on what's going on in terms of the powder for future operations.
All right. I have a couple of questions here that relate to gaining access to the data set, such as price and limitations on the license. Is that something that they should contact you directly to have answered?
Yeah, we'll take that offline, but we'll be glad to work through that with folks.
Right. So, can you tell me a little bit about HIP, hot isostatic pressing? And did you do that on all of the samples? Is that sort of a requirement for this testing?
Yeah, I can take that. So there's quite a bit that goes on. So hot isostatic pressing is a form of heat treatment where you have high pressure argon um, in a pretty massive pressure chamber. I think it's on the order of 15,000 psi of argon that you're doing that heat treatment at 900 degrees Celsius. So there's a couple of reasons you want to do this. It's certainly not a requirement, but it's been something that has certainly been built into the additive process for quite some time now, especially with laser powder bed fusion. And the idea is you use this high pressure gas to actually kind of close some of the smaller pores within the material. So you increase the density of that material just a little bit. We're talking fractions of a percentage usually. And then the heat treatment is kind of secondary along with that to help reform your grains, relieve some of the stresses. You typically, especially with titanium, have quite a few residual stresses that are built up throughout the additive manufacturing process. So HIP is able to both relieve those stresses, close out some of those pores, and just give you some of that kind of more refined grain size. Mike's the metallurgist here.
Yeah, so I'll just add to what Ryan said there. So I mean, it's another choice in the data set, right? So the hot isostatic pressing, the DMP process really prints pretty darn dense titanium, right? So at the end of the day, as it comes out of the printer, you're probably talking about material that's 99.8 some odd percent dense, right? So quite dense coming out of the printer per pixel density. So you're pretty dense coming out of the printer, but sometimes you want to close up that last little bit of porosity. That can be particularly helpful in fatigue sometimes. So you do that with the hot isostatic press process, and that's going to allow you to close up the vast majority of internal porosity that isn't surface connected. So so that's a choice. One of the other choices, you can use these if the residual stresses are not objectionable in the print. You can actually use these right out of the printer, and sometimes you'll actually have even a higher strength condition coming out of the printer. And we do have some customers that do that as well. With respect to the data set, we had to make some choices about what was going to be center of mass for the user community. And so what we've found with most of our customers across aerospace and healthcare is that the majority of them are using the HIP process with titanium. So for the material condition, for the heat treatment that we're going to document inside this data set, we made the hot isostatic pressing determination. But you don't necessarily have to do that. It's just going to be a very common choice.
Okay. A number of questions. So how do you show the flexural properties such as yield strength, UTS, fatigue life, and compare that to forged titanium, 6 aluminum, 4 vanadium?
So the data sets that we presented today. Ryan, do you want to go back to the monotonic data that you introduced, the box plots? So here you'll see the box plots associated with the data sets. So in each one of these box plots, that's a statistical representation of the data set. Almost 400 tests here are represented on these 4 plots. So historically, other databases, they have had many tests that were used to generate similar types of data sets, right? So on this particular plot for UTS, 2% offset yield strength, and then two representations of ductility, elongation to failure, and reduction of area. Those data sets, the largest data set is going to be the AMS 4911 reference line, which is somewhat below the data set that we've presented here today. So there is a reference, which is Mill Handbook 5 Rev J. So that is a historical set of databases and design information. That's a very similar testing exercise to what we've presented to you today. So there are hundreds and hundreds of tests behind that line there. And so that is one data set that we've pulled from the literature. There are others. But the reason we selected that particular data set to make the comparisons with are information that is in the Mill Handbook 5 or its successor, MMPDS, or some of the other databases like those that are curated by NIAR with the NCAMP process. Very, very highly pedigreed, similar to what we've presented to you today. And so that is a lower bound type behavior there, determined by many, many tests. And that would be comparable. We would compare that to the lower bound whisker there for the box plot, as Ryan is highlighting now. I think it's really important to recognize that these microstructures are not directly comparable, and the heat treatment and overall heat and beat metallurgy that you use to get to these different microstructures, there's important differences there, but we're just comparing statistically significant mechanical properties.
All right. Can you talk a little bit about fatigue tests at different temperatures? Is that important? Say all the way up to 500 degrees Celsius?
So for the particular data set that we've presented today, we didn't do that higher temperature fatigue testing. So we're doing room temperature testing. So testing up to 500 C, that would be a little bit sporty for TIE 6.4. You could conceive of design activities that might get you to 200, 250 C, maybe for TIE 6.4. So between cryogenic and 250 C, depending on the application, there might be useful data to be generated there. We did have to make some hard choices when we were getting into the fatigue testing. For those of you who do this for a living, I think you'll recognize there's infinite time and money in testing that you might get involved with in fatigue. And so we figured that we would make, again, center of mass. If you're going to run one test, you're going to run probably room temperature testing, and you're going to run a stress ratio of -1, which is fully reversed. But there are a range of other tests that you might run in that space, including testing at elevated temperatures.
All right. I'm trying to combine a couple of questions here. So a number of them have to do with HIP, whether that's required or what if they don't normally do that. Is any of the data set applicable to their results?
So I think that what you would want to do is you would want to supplement the data set with non-HIPed data to make sure that you are getting representative tests. Depending on the application, you may want to rerun quite a bit of data and make sure that even if you're not getting exactly the same numbers, you're getting, I'll just say similar trends. But for non-HIPed applications, certainly you're not required to HIP. It's just most aerospace customers and most medical devices, most of those are going to be HIPed.
All right. With all of the new materials coming out, if they have slightly different recipes from the grade, is the data set applicable to those, or will you have to run something customized for something that's even slightly different?
Well, the short answer is you may need to run new data sets if there are important differences. If there are not necessarily important differences, if you're running in a little bit different configuration in the machine, or maybe you're doing multi-laser or something like that, you can run what's called a delta qual, and you can run a subset of the tests, and you can and from that subset of the tests, you can infer if there are statistically significant differences in the properties that you're getting versus the ones that we've reported here. So the short answer is yes, sometimes you're going to have to run more tests, and that's because things really are different. And you need to, to make sure that you capture that in your allowables data.
All right. Were you or did you conduct any other post-HIP processes, and such as cleaning or other process? And do you have any analysis for unbonded particulates for the test articles?
So that that wasn't a part of this test campaign. So after the parts came back from HIP, I mean, before they even go to HIP, they are depowdered using compressed air, and we have a depowdering procedure. Once they go to HIP, or excuse me, once they come back from HIP, the only post-processing that's done on the parts is just removing it from that build plate, separating those stacks, essentially just getting those samples prepared for machining. In the case of the data you have here, if there was anything on the surface, it would be machined away anyway. With all that said, speaking at just projects that are external to this, 3D Systems does quite a bit of testing with titanium. We do a ton of medical devices where particulates, especially surface, potential contaminants or FOD, is cleaned off and tested. That's a huge part of FDA requirements for medical devices, and that's something that we have a ton of experience with and don't usually see any problems with.
All right. You showed the test builds at vertical, horizontal, and diagonal orientations. Was there much difference in any of the outcomes for the tests based on the orientation that they were built?
Yeah, great question. There was not any significant difference. So that's getting back to that practical difference. Very, very small differences in the means between those. So even though, in kind of the as-built condition, they are kind of growing a little bit differently, partially due to just the densities that Mike mentioned within the additive manufacturing process, and then partially due to some of that heat treatment. You see quite a bit of isotropy after those processes.
All right. Is variability from process parameters such as laser speed and power considered when generating these data sets?
So we did not do that for this data set. Part of what that is, it is partially incorporated within this in terms of our pre-qualification. So all of the machines were qualified using something called an operational qualification. This is something we do for just making sure that our print process is producing material that we meets all of our specifications, even at our kind of worst case conditions. And that is one of those where you're, generally speaking, you can either change the speed or the power, and they have some slightly different effects, but ultimately it's about the energy delivered to the spot within the powder bed. And so that's something that we do test. We did not have that as part of this. It's part of our validation procedure, though here we wanted to have a qualified process. The idea is you've got a process that is pre-qualified and you're generating inherent variation and statistical confidence within a qualified process.
Yeah, this is just to add to that, the results you're seeing here, this is for our fixed commercial process, right? So if you buy a DMP 350 system like we showed you earlier, configured for titanium, all of the build parameters and all of that are completely incorporated, right? So you would get very, very similar results. And that's a fixed process. There are other choices you can make, right? So you can, with the ultimate version of the software that comes with this, you can change all of those knobs on the laser powder bed fusion process. Not that I would necessarily recommend getting too far afield, but there are many, many processing parameters that are available to be tuned inside laser powder bed fusion. Those are fixed for this particular operation.
All right. Could one of you explain a little more about the use of coupons on the builds to indicate quality compared to actual part testing?
So this is a complement to what you would do with part testing. Making sure that you can build statistically significantly good and reliable metal is part of that, right? You have to be able to do the mechanical testing in a reliable, repeatable way. That's where the coupons come in. As you were getting into components, then if possible, sometimes you can excise representative coupons from the parts themselves. So subsize mechanical testing coupons, things like that. And then of course you can also look at things like microstructure and density and so forth. So we do have some history with that, with working with customers that are building, big serious parts to do big serious things. And we've had very good agreement between what we do with the coupons and what we do with the parts. I'll put one caveat on that. As walls and structures get very, very, very thin, you start to see differences in mechanical properties from what we're showing you here.
All right. I want to go back to the talk about the amount of oxygen. You mentioned from less than 5 parts per million up to about 25 parts per million. Are your results consistent within that range?
Yeah, so we don't have necessarily like a wide range of the chamber oxygen as part of this. It's all pretty consistent typically. I don't have the numbers right off the top of my head, but I can just tell you from my own experience of running all of these builds and many dozens of others that you don't see any significant difference when you get down to that level. If you are in maybe like the hundreds of parts per million, if we're just talking kind of orders of magnitude, that is where you start to potentially see some changes, but it's usually several orders of magnitude above where we're at.
All right.
You do see some differences between different machines. So part of our DMP process is making sure to pump down the chamber and getting to that really low oxygen environment. The systems themselves, they alarm at 25 ppm. And if you look at the whole range of laser powder bed fusion machines, many of those are not going to do that same low oxygen architecture, and they're going to be operating at hundreds of ppm, even higher than that, right? Blowing just high purity argon or nitrogen in some cases. So we're going to get maybe a little bit different results in terms of the chemistry of the base metal. That's really important to making sure your part is, actually grade 23, does have that low oxygen, that low interstitial content. And then it's really important to making sure that you can use that very expensive titanium powder to the powder lot exhaustion.
All right. Are you going to be using these tests on other grades besides 23 to fill out the data set?
So we're gonna so right now grade 23 is, I'll just say that's the most popular by a very, very significant margin. And so as and when customers are requesting other materials, we'll be doing, we may be doing other materials cooperatively.
You dropped out there, Ryan. Could you repeat that, please?
Yeah, so tie grade 23 is kind of center of mass for what our customers are asking for. But as there's more customer demand, we may take a look at doing other materials.
All right, thank you very much. Well, we're about out of time, so thank you, Mike and Ryan. Thanks again to our sponsor, 3D Systems. 3D Systems offers a broad portfolio of additive manufacturing hardware, software, materials, and service solutions from plastics to metals. Their global application innovative group reduces risk and creates a faster return on investment for customers by developing qualified, transferable, and scalable production processes. Be sure to register for our upcoming free webinars at the resources menu tab of our websites on the drop-down events link. If you have any comments or suggestions, please email them to me at ebrothers@gie.net. On behalf of Aerospace Manufacturing and Design, I wish you a good day and goodbye for now.
You can find more Manufacturing Matters plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcast, or on our websites at todaysmedicaldevelopments.com, aerospacemanufacturinganddesign.com, and evdesignandmanufacturing.com.